All right, in problem 20, we have a medical center that conducted a study to investigate cholesterol levels in people who have had heart attacks. A random sample of 16 people was obtained from the names of all patients of the medical center who had a heart attack in the previous year. Of the people in the sample, the mean cholesterol level was 264.7 milligrams per deciliter, with standard deviation of 42.12 milligrams per deciliter. Assuming all conditions for inference were met, which of the following is a 90% confidence interval for the mean cholesterol level in milligrams per deciliter of all patients at the medical center who had a heart attack in the previous year? Okay, so let's see what we got here. We have a sample of 16, so N is 16. Whoa, N is 16. We got a sample mean of 264.7 and a standard deviation of 42.12. And we want to find a 90% confidence interval. So let's recall what our confidence interval form is. Remember, it's the point estimate. In this case, it'll be sample mean plus or minus the critical value. It'll be this case will be T star times the standard deviation of the statistic. In this case, it'll be the formula, standard deviation of X, the population standard deviation divided by the square root of N. And now, if you forget like these formulas, you should understand the general concept, but the formula, not a big deal because you got your formula sheet here. And they even give you like a breakdown of the confidence interval. So here you go, just know where to look. So let's fill this in what we got so far. So we got 264.7 plus minus, we have this, we have sample mean, which is N at 16. We have to find T star. Now, our critical value is T star, but remember that when you have a T distribution, you have to have degrees of freedom. Degrees of freedom is one less than the population, or one less than the sample size. Remember, it's N minus 1, or in this case, it'd be 15. So from there, you look at your table. And again, this will be in your formula packet. T distribution, a T star value with degrees of freedom 15, where you have 5% to the left and 5% to the right, because that'll be a 90% confidence interval. And luckily, it even tells you which of these match up with the 90% confidence level down here. So we're going to look in this column, lining up with the 15, and you'll get the 1.753. So your T star is 1.753. So we're going to have 1.753 here times 42.12 over the square root of 16, or over just 4. So now we just do a basic calculation and leave this to your calculator. So this will be simplified at 264.7 plus minus 18.45909. And from there, we add this value to that, 264.7, and we subtract it from that as well. So 264.7 minus 18.45909. That's the lower bound. 264.7 plus 18.45909. And we'll get the upper bound. So our confidence interval will be 246.24091 to about 283.15909. And so that looks like it'll be C. So our answer is C, right? Right, 21. This is a cool one. Probability. Okay, so for a school fundraiser, 600 raffle tickets were sold by students at the school, of which 88 were sold by one student, Audrey. Of the 600 tickets sold, 30 were randomly selected to receive prizes, and 7 of the 30 tickets selected were tickets sold by Audrey. To investigate how likely it was by chance alone that at least 7 of the 30 selected tickets could have been sold by Audrey, students in a statistics class ran a simulation. Nice. One trial of the simulation is described by the following steps. Step 1. From 600 chips, assign 88 red and the rest blue. Step 2. Select 30 chips at random without replacement. Step 3. Record the number of red chips in the selection of 30. And here we got the results of 1,000 trials of the simulation and the histogram. Okay, so the question is now, based on the results of the simulation, is there convincing statistical evidence at the significance level of 0.05 that the event of Audrey selling at least 7 of the 30 selected tickets is unlikely to have occurred by chance alone? Okay, so let's see, based on the simulation, what's the probability that we would have had 7 or greater red chips when you selected 30? So the probability, let's call these x, probability that x is greater than or equal to 7. So we just want to count how many are in here, 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 and here, and here. Add these up and divide it by the total number of trials, which would give us a probability. So we would go 78 plus 39 plus 15 plus 5 plus 1. 138 divided by 1,000. We should know it's 13.8%. We get 13.8% or 1.38. So the probability of selecting 7 or more red chips simply by luck alone is almost 14%. It's 0.138. So this basically is, reasonable evidence that it's reasonable to think that Audrey would have had 7 of the 30 tickets that were randomly selected, because this has a 13.8 chance of occurring based on the simulation. So we shouldn't be suspicious of Audrey. And so then it would be E. All right, let's look at number 22. Reading one. All right, it's part of a study on facility needs. The administrators of a university want to estimate the percent of students who use exercise facilities on a regular basis. From the 34,000 students who attend the university, a random sample of 370 male students and 400 female students was selected. Of the 770 students selected, 493 students indicate that they use exercise facilities on a regular basis. What are the population and sample of the study? So this doesn't seem hard. Hopefully it isn't hard. So the population, remember, is the group of individuals we want to study. So they are looking to estimate the percent of students who use exercise facilities on a regular basis. So the population would be all the students in the university. And so it would be all of these. This would be like the population of 34,000 students. And the sample is the group that we selected at random. We selected 370 males and 400 females, but in total we selected 770. So that would be our sample. Let's see which of these fits this description best. The population is 770. Nope, that's definitely not it. Not A. The population is 770 students. Nope, but not B. Population is 34,000 students who attend the university. Okay. And a sample is whether each student in the university. No, that's wrong. D, the population is 34,000 students who attend the university. Okay. And a sample is 770 students who were selected. So the answer looks like it's going to be D. Let's just check E for good measure. The population is 34,000 students who attend the university, and the sample is 493 students who indicated that they use exercise facilities on the regular basis. So this doesn't have to be necessary for it to be the sample. The sample, includes, all of them, this would be like this would be the proportion of students from the sample that would, or like the number of students from the sample that would use exercise facilities on a regular basis. So it's not E either, but it's definitely, so the answer is definitely D. All right, 23. A study will be conducted to examine a new medicine and they intended to reduce high blood pressure in adult men who have high blood pressure. As part of the study, a random sample of 40 men with high blood pressure will have their blood pressure measured. So 40 men, so N is 40. And then they will take the new medicine every day for 1 month. At the end of the month, their blood pressure will be measured again. The following, which is the best procedure to investigate whether there will be convincing statistical evidence of a change on average in blood pressure for men with high blood pressure who take the new medicine. Okay, so if we have our individuals, let's say we have, our values for, we have 40 men, we have individuals 1, 2, 3, 4, 5 all the way. And then from each individual, what's going on is we're taking 2 statistics, or remember, we're recording 2 values. We're recording the blood pressure they will be recording their blood pressure at the beginning, and then we're going to record their blood pressure at the end. So we say begin, end. So let's just say, for example, candidate 1 has, let's say 140, and this one will be at the end 130. And then this one has, let's say 150, and this one, it ends up with 140. So each individual has 2 values recorded, the blood pressure at the beginning and the blood pressure at the end. And then we calculate a difference. In this column, let me use this green color. We calculate a difference in blood pressure from the beginning to the end for each individual. Let's say 140 minus 30, 10, 150 minus 40, 10, so that sort of thing. So we're basically only going to have a 1 sample test because our sample are those 40 men, even though we're recording 2 values for each of those. So it's not going to be anything that says 2 samples. So neither of those. And so the question is a matched pairs t-test for a mean difference or a chi-square test for independence? Well, let's look at what we're recording. We're recording basically on average the blood pressure change to take the new medicine for if there's a blood pressure change on average for these individuals. So the blood pressure is measured in an actual a value, like a quantity, like a whole number or maybe a decimal, but I assume whole numbers. So we're not looking at proportions. We're looking at basically the difference in means. So it's not going to be A, and it's not going to be chi-square. This is for categorical variables, and the answer will then be D, a matched pairs t-test. So a reminder, what is a matched pairs t-test? That's essentially when each individual gets both treatments. In this case, the treatments are you could think of as the blood pressure measured at the beginning and the blood pressure measured at the end. And so the answer will be D.